Good morning everyone, I'm Francesco Fabiano and today I'm going to present you EFP 2.0, a multi-agent epistemic solver with multiple state representation. This is a joint work by me, Alessandro Burigana, Agostino Dovier and Enrico Pontelli, and is a joint work also from University of Udine and New Mexico State University. So this is just a quick outline of the presentation. First of all, we're going to introduce some basic notion of multi-agent epistemic planning. Then we're going to proceed and explain a new epistemic state representation. After that, we're going to present you the contribution of the paper, and then we're going to conclude the presentation. So what is epistemic reasoning? Epistemic reasoning is the kind of reasoning that is not only about the physical world, but also about the agent's knowledge or beliefs, and also about the agent's knowledge-belief relation. When this type of reasoning is applied to the planning problem, we have multi-agent epistemic planning problem. In this setting, we have plans where the goals can refer to the state of the world or the knowledge or belief of the agents. But more in general, we also have all the formula that can be founded in a planning domain can be referred to these two concepts. Okay, we can now introduce the epistemic state representation that we use through our work. If you know epistemic reasoning, you know that usually an epistemic state when multi-agent reasoning is involved is represented through a cryptic structure. In particular, a cryptic structure is a graph directed and labeled where each node corresponds to a possible word and the edges are used to encode the beliefs of the agent. You can see a cryptic structure in the bottom right of the slide. Nevertheless, in 1997, Gerbrandi and Graneved introduced the concept of possibilities. Possibilities are a data structure based on non-bounded set theory that are suitable to represent multi-agent information change. You can see a possibility on the bottom left of the slide and the corresponding system of equations in the bottom center of the slide. The beauty of possibility is that each possibility corresponds with a class of a similar cryptic structure, allowing for epistemic state to be always compact. But more formally, what is a possibility? A possibility is just a function that assigns to each propositional variable a Boolean value, a truth value, and to each agent a set of possibility. That is why possibilities are not well founded. And this set of possibilities, called information state, is used to encode the agent's belief from that possibility. Starting from the concept of possibilities, in 2019, we also introduced a new epistemic action language, MIRO. This action language is a modification of MI* that was introduced by Baral and others in 2015. As MI*, also MIRO is able to comprehensively reason on unlimited nested knowledge or belief, and also common knowledge or belief, depending on the constraint that we have on the underlying states. And it also introduces three types of action: ontic, sensing, and announcement. Ontic is the action that resembles the most classical planning. The ontic actions are the ones that allow the agents to modify the word, while sensing and announcement are called epistemic actions. Sensing is an action that is used to refine the knowledge or belief of the agents, while announcement is used to share information with others. One last concept that is introduced in these two action languages is the idea of awareness of agents. In particular, an agent can be fully observant with respect to an action when she knows everything about the action execution, so the execution and the effects of the action; partially observant when she only knows that the action has been executed without knowing the effects; and oblivious when she is ignorant about the action, the execution. Let us now proceed and introduce the contribution. The first contribution we provide is the update semantic for MIRO. Basically what we did, we redesigned the semantic of the language, making it more compact and clean, and this brought us to a more efficient implementation of the language itself. We also demonstrated that MIRO transition function respects some fundamental properties of multi-agent epistemic reasoning. These properties involves the updates of the beliefs of the fully observant, partially observant, and oblivious agents and their relations. As a second major contribution, we introduced the Planner EFP 2.0. EFP 2.0 is an epistemic forward planner that is based on a complete code rework of the Planner EFP 1.0. This planner was introduced by Lee and others in ICAPS in 2018. As his predecessor, it uses breadth-first exploration to explore the search space, but contrary to EFP 1.0, it allows for multiple state representation. So with EFP 2.0, one can choose between cryptic structure and the semantics of MRO, or possibilities, and the newly introduced semantic that we presented in this paper. Moreover, we allow the planner to reduce the size of the structure using the Page-and-Tarjan algorithm. This will allow the e-states to be always compact and compressed. And we introduced the idea of already visited e-state. This is a concept that is quite common in planning, but was never introduced for epistemic planning. As a side note, if you are interested in the planner that is written in C++, please mail one of the author and ask him the source code. We will be happy to send you all the code and the material to try and play with the planner yourself. We are now finally ready to introduce some experimental evaluation. So in our work, we compared several configurations of EFP 2.0 with each other and also with EFP 1.0. We compare those only with EFP 1.0 because it's the only other comprehensive epistemic planner that can be found in literature. As we can see from the coin in the box domain table, PMAR, the configuration that exploits possibilities, is the fastest one by order of magnitude with respect to the same planner using cryptic structure and also with respect to EFP 1.0. You can see here that WP means wrong plan. That is because EFP 1.0 had a bug in the initial state generation that we corrected in the EFP 2.0. Looking at the assembly line, we have also some other performances comparison. Here also we can see that PMAR outperform all the other configuration in EFP 1.0. The interesting part is that the depth of the knowledge doesn't affect PMAR as bad as the other configuration, and also that the common knowledge operator in the common knowledge operator PMAR maintains its performances. Another comparison that we performed was between the configuration of EFP 2.0 when the visited state check is activated or not. As we can see from the table of the grapevine domain, the activation of the visited state check really helps in the searching task, especially when the domain rises in complexity. This means that the epistemic state check is really helpful, especially when the domains became really complex. One last comparison that we're going to present is the comparison between EFP 1.0 and the best configuration of EFP 2.0. As we can see from the graph, EFP 2.0 really outperformed EFP 1.0 by order of magnitude. This is due to the optimized transition function, to the visitor state check, and to the use of possibilities as e-states. So, to conclude, in this paper we presented EFP 2.0, an epistemic forward planner that provided significantly better results with respect to its predecessor, EFP 1.0. EFP 2.0 is able to outperform the state-of-the-art, the previous state-of-the-art, by using possibilities, dynamic programming, reduces size of the state, and thanks to the code refactoring of the EFP 1.0. Moreover, we also provided a new formalization of the transition function on which EFP 2.0 is based, along with some desired properties of that transition function. Still, there is a lot of work that needs to be done in multi-agent epistemic reasoning. First of all, we need to consider possible symbolic representation for each states to improve the planning times. We also need to formalize the concept of non-consistent belief and the ideas such as trust, license, and misconception. These 2 points could really help in widen the possible scenarios that can be represented through epistemic reasoning, multi-agent epistemic reasoning. And finally, we need to formalize and construct heuristics to really help the planner scales. That's all for the presentation. Thank you.